And welcome to Lab 5 of Physics 2211, Collisions. Okay, so let's start with the introduction. The purpose of this lab is to analyze the motion of a rolling object as it collides with a stationary object before and after collision. So we're going to put the data in Tracker and then code the predicted model using GlowScript. Okay, so what are our main concepts for this lab? Well, we have the conservation of momentum, which is the total momentum of a closed system is equal to the total momentum of a system after collision. We also have Newton's second law, which states that an object's acceleration is directly proportional to the net forcing acting upon it. We have elastic and inelastic collisions, which is when momentum and kinetic energy are stored, that is an elastic collision, and when they're not stored, it's an inelastic collision. Okay, so these bring us to our equations. First, we have our conservation of momentum equation, which is the change in momentum total equals to 0. And this can be simplified to P1 plus P2 initial equals P1 plus P2 final. We also have our velocity and position update formulas. These will be particularly used in the GlowScript code. We also have our kinetic energy, which is half mv squared. And we have our Newton's second law, which is the change in momentum over change in time. And since there's no net external forces, we can make this equal to 0. Our major assumptions are that the major external forces acting upon the object happen quickly and are negligible, and the motion in the y and z direction are also negligible. Okay, so here's our experimental procedure. We're going to record a video of an object colliding with an object of the same type, and our object will be expo markers. We're going to import the video into the Tracker program, get the data, and then create a computational model for that data with our initial conditions. And then we're going to compare our charts and make final conclusions about if it's an elastic or inelastic collision. So our system is both of our masses. Our surroundings are everything around that mass, like the table, which has like friction, could potentially have friction. We have our preview or final results is that our collision is inelastic. So here's our experimental procedure. On the left, we see our video that we import into Tracker. We put all of our calibration stick, our axis to basically set it up. Our initial conditions are our initial velocities of both of our objects, which is basically calculated by doing the slope of the lines for mass A and mass B. We also get our object's mass, or we also know our object's mass. So here's our computational model for where we put our initial conditions in. We put our ball 1 and ball 2 mass. We also put the position and velocity initial values for both. This is the main part of the code, which is the while loops. We take the while loop before and after the collision. Before the collision, it's up to 0.333 seconds, and after the collision, it goes up to 1.67 seconds. We'll be using our position and velocity update formulas in these while loops. So what do our results give us? We're on the left, we have the results from the GlowScript code, and we see kind of straight lines after our collisions. And it's very similar to our actual data, which is seen on the right from the observed data. But as we can see, the observed slightly differs towards the end of the collision, kind of tending upwards a bit. But they're very similar. So what are the sources of error that lead to that? Well, there's human error using Tracker, like the point masses, and we also don't account for external forces like friction and air resistance that could potentially affect our values. So for my first question, it was, for your model system, is the kinetic energy conserved? So how to do this? Well, I first found the initial and then I found the final, and I checked if it was conserved. So our initial kinetic energy was just half mv squared for both masses, and it came out to 0.0022 joules. For the final kinetic energy, it was 0.0002 joules. The difference in percentage was negative 0.89, and since it's negative, it indicates that K was not conserved, but rather lost. Kinetic energy was lost. My second question was, what if the initial speed of the striking object was doubled? Since K is half mv squared, kinetic energy is directly proportional to the velocity squared, and a larger initial speed would quadruple the kinetic energy, which would lead to a larger difference between final and initial kinetic energy, which also means that it would be more of an inelastic collision and less of an elastic collision. And finally, what are our conclusions? The predicted and observed models have very similar graphs, and the collision is inelastic because kinetic energy is lost. Thank you for watching my video.